Okay, so welcome back. We were discussing Wang-Landau algorithm, which calculates the density of states of a discrete model. And the idea is that the energy levels the number of energy levels is much smaller than the number of configurations. And if we can walk through the energies of the system, it might be much more efficient than walking through all possible configurations of the system. And this is sufficient to calculate any thermodynamic quantity. And in this way, we can then simulate much bigger systems than if we simulate directly the model, such as Ising model or any other model that has discrete energies. So we coded the algorithm last time, and the code here was running for some time, and we were obtaining logarithm of density of states by multiplying the logarithm of density of states by multiplying the density of states whenever we visited particular energy. And then we reset the histogram whenever we see that the histogram becomes flat, and then we reduce this modification factor in such a way that in the last iteration, the modification factor is very, very close to 1, which means that we're almost not changing the density of states anymore. We're multiplying with some factor, which is very, very close to 1. And now the question is whether this actually gives a decent density of states. We understood by just looking at the way we obtained the density of states is that this is only correct up to a normalization factor. So we need to normalize the density of states properly. And then we realized that the two endpoints are always doubly degenerate in this model. Therefore, we can use this to properly normalize the density of states. Although even if the density of states was not properly normalized, this wouldn't be necessarily a large problem because most of thermodynamic quantities do not depend on normalization of the density of states. Now, so with this, we determined this constant LGC, with which the logarithm density of states had to be normalized. The density of states has to be normalized, or logarithm of density of states has to be just shifted in energy. And then we plotted this logarithm of density of states. We see that this value in the center where there is large degeneracy is very large, of the order of e to the power of 250, and of course at the edges should be 2. And then we said that from this we can calculate thermodynamic quantities. We said that average energy, specific heat can be calculated, and I also added today entropy. Okay, so which is maybe slightly harder to calculate, but nevertheless it's completely straightforward. Now I did not quite explain how these thermodynamic quantities are obtained, although in some sense it's something that most of you are probably familiar, because it's basically just a standard thermodynamics problem. But I prepared here the summary of how to calculate thermodynamic quantities for this case. So we said at the beginning of this Wang-Landau chapter that free energy is minus T times log Z, where Z is basically this density of states times e to the minus C over T. Okay, so again, how do we know that? Well, by definition, of course. Let me stop here. Let me move this down. So by definition, we know that Z is equal to sum over all configurations, e to the minus e of x divided by t. But then we introduce density of states such that when we integrate over energies only, then we can write e to the minus e over t times the degeneracy of each energy. Okay, and the degeneracy of each energy is density of states, isn't it? So the alternative way to write this is to say that, so what did I use this, is that, yeah, this G of epsilon. So what I want to use is the following, that we can also say that G of epsilon is equal to sum of all configurations, delta of epsilon minus E of x. Okay, so basically, this is to say the density of states is basically just counting how many states we have at particular energy E. Okay, and now if you insert this G of E into here, for example, then you will obtain, of course, exactly this. You obtain exactly this original configuration, e to the minus ex over t. Okay, so so if you accept that z is this, okay, then this is the definition of the density of states, and then we see that basically these two ways are equivalent. Now, so this is a standard thermodynamic relation. F is minus T log Z, and we have this. We know now Z that Z is this. Then we can also write the thermodynamic relation that free energy is total energy minus T times S, where S is entropy, T is temperature, isn't it? So this is another standard thermodynamic relation. And yet another standard thermodynamic relation is that dF is minus S dt minus P dV. Now, again, this comes simply from the fact that the average energy is T ds minus P dV, doesn't it? So if this is true, okay, well, of course this is true, so that's how it works. dE is T ds minus P dV. Then when we take the when we write dF here as that dF is dE minus ds dTs minus T ds, and then we get this relation that dF is minus S dt minus PdV. So again, S here is entropy, dt is temperature, and then we have this PdV, but we are working at constant volume, so therefore this term vanishes for our case. Okay, so now if you know this, the question is how do we calculate these quantities? Well, entropy is basically just here we see the formula. So at we're working at constant volume. So entropy then is just dF over dt at constant volume with minus. So that's equation, isn't it? From here we can get this. And then all we need to do is to take the derivative of f with respect to t. Well, here is the formula for f. We take the derivative with respect to t. So what do we get? Well, when we take the derivative with respect to t, we first take the derivative with respect to this t here, and we get minus log z. And then we take the derivative with respect to this t here. To this t here, what do we get? So then we get minus t is left, doesn't it? And then we have this logarithm of z is basically 1 over z, and this thing is dz over dt. Okay, so we just arrived at the equation then that entropy is log z plus 1 over z times, now we can take the derivative of dz over dt, which is derivative of this thing with respect to t. Okay, and this is very easy to do. So we have g of e to the minus e of t, and then when we take the derivative with respect to this to the t, we get e divided by t squared, isn't that? But there is one t in front, so therefore it's e divided by t only. Okay, so basically I just took derivative of this dz over t. So this is just direct consequence of writing free energy like that. And then we can rewrite, of course, this as log z, and this quantity here, we recognize that basically this quantity here is basically just the average energy. No, actually with z. So this part here is the average energy divided by t. Okay, so that's another way to write it. Entropy, and that's something that we're going to calculate. And now we can, now that we have entropy, so this was the first quantity we calculate from derivative of free energy. Now we can calculate back, or we can check how the total energy looks like. So the total energy is, of course, then from this equation is F plus T times S, isn't it? So total energy is F plus T times S. So this is the same. This is 1 to 1, isn't it? So F is E is F plus T times S. So we said that F is equal to minus T log Z. So this is this part. And then we add plus T times S, but as we just calculated. So then means is this thing is plus T times log Z. And then we multiply this thing with T and we get this. Okay. And now we see that this and this cancels and we get this 1 over Z, sum over density of states, e to the minus ct times e. So, and this quantity, yeah, so it's this quantity. This is the relation for average energy. And we said, yes, of course, but that's what we derived a long time ago, isn't it? And it's kind of obvious because we said that the average energy, when we write this in terms of configurations, so if we go over all possible configurations, then of course the average energy is just, so this should be average energy. So the average energy is just 1 over Z times sum over all configurations, e to the minus E of X divided by T times average of X. But now, since we know that the density of states just counts the degeneracy, of these energy levels, and that's how to write the degeneracy of the energy levels for density states, then we can write that the total energy then, so the total energy is then clearly just 1 over Z degeneracy at each energy level times E to the minus E over T. And if you want, you can then insert this definition for the density of states in here, and you will immediately get this equation. And from this, you can then eliminate density. You eliminate the delta function by summing over all delta or epsilon. So this gives you 1, but you need to replace then epsilon with d of x and epsilon with d of x, and you get this. So I just proved that basically this equation here, with which you started, is equivalent to this equation. Of course, these two in some sense are obvious, but I'm just proving something that's kind of obvious. Now, finally, specific heat. There are 2 ways to derive specific heat. One is to say that specific heat is just dE over dt, but we can also check another standard thermodynamic relation from entropy. So we know that CV is also TdS over dt. Now we can then check what is S. I mean, this is our S. We insert this in here and we can check. So we can take then T ds over dt is derivative of log z with respect to t, and derivative of log z with respect to t is 1 over z dz over dt. Then we need to take the derivative of this quantity with respect to t. Now, when we do that, we see that, we actually, it's better to look at this equation. So we took the derivative of this with respect to t, which is 1 over z dz over dt, but then we also need to take derivative of this with respect to t. And when we take derivative with respect to 1 over t, here we get 1 over t squared times average E. And then we also require to take the derivative of this quantity, d over dt. So we have 1 over t e over dt, and then we see that these two cancel, and then we have t and 1 over t that cancel, so the result is dE over dt. But that's exactly the thermodynamic relation that we used the last time. And then, of course, we have the definition of our average energy, which is this quantity times E. And then we take the derivative of this and we get E squared over T squared. And then also this other term. So this derivative we already performed last time. And we see the specific heat is then can also be written as average E squared minus average of E squared divided by T squared. Okay. So in summary, in this derivation, we started from free energy being expressed as minus T log Z, and then using only standard thermodynamic relation that F is minus total energy minus T times S, we managed to obtain entropy expression for the entropy. We managed to obtain the expression for total energy, which of course we knew before, and also expression for the specific heat. Okay, now knowing all those three relations, then we can properly code thermodynamics, and here's the code. So we in EV. So yeah, first we're going to loop over all energies here. So we enumerated all energies before, and we calculated what is logarithm of density of states for each energy. And then we are going to kind of calculate kind of Z for each configuration. But it's not exactly Z. And the reason for this is because Z could be extremely large, even for one degeneracy, like Z for the state with zero energy could be so big that that we could get overflow. So therefore, what we are going to do is we are going to calculate Z divided by Z naught, where Z naught is the Z for, let's say, ground state. I mean, here we could choose any state. We could state Z naught is Z for the lowest energy. Yeah, so state with the lowest energy, with the ground state. Of course, that in some sense it's our choice. We could take also some other state, but just the important thing is that we normalized with something so that we try to avoid the overflow. Okay, so this weight here then is kind of Z divided by Z naught, where Z naught is Z that corresponds to the ground state. So therefore, we have for the average energy to the power of n is basically then E minus minimum energy, which corresponds to the Z naught divided by T, and then times density of states of E divided by density of states of the ground state. Okay, and then we need to divide the entire thing by 1 over Z, by 1 over the exact Z actually. Okay, by the exact Z. No, but this was actually correct. We need to multiply by Z naught because this thing is divided by Z naught. So therefore, the Z naught here and Z naught in the exponents inside the sum will cancel. So now this W here is exactly this. But actually this is wrong. So it needs e to the power of n. So what I wanted to say is that this W is exactly this G divided by G0, e to the minus E min over T. So how do we see that? Well, we are storing logarithm of the density of states. Therefore, G of E divided by G0 is actually exponent of the logarithm of density of states at particular energy E minus logarithm of density of states of the ground state of zero, isn't it? So basically this ratio here is exactly the same as this exponent to the log EI minus log E0. And then we also need to add this in the exponent, which is E minus E min, isn't it? This is E minus energy of 0 divided by T, okay? So basically this entire expression up to here is encoded in W. And then for now, Z is gonna be just sum of these weights, and then of these weights, and then at the end of the day, we can calculate, we can change Z by multiplying with Z0 for the ground state. Then the average energy is going to be just this weight times Z. So we're multiplying here times E times this weight. So this is what we call EV. And then E2V is basically just taking E square here, E to the power of 2. And then at the end of the day, we multiply. Well, no, actually we divide by what we call Z. But this quantity, actually W, basically this, what we call Z here, what we call this Z here is basically Z divided by Z0 already, okay? So therefore, if we divide by Z divided by Z0, which is the same as multiplying by Z0 over Z, we get exactly total energy, we get square of total energy, and then specific heat is E square minus average heat over T square, isn't it? So with this, we already calculated these three quantities: total energy square, and specific heat. And now we want to add the entropy. So the expression for the entropy I just derived today here. So the entropy is, I guess, the best way to do it is to look at this expression. So it's log Z plus 1 over T times average energy. Is that log Z 1 over T average energy? So how do we calculate this? So it's like Z correct. I call it correct because this is the real Z, not the Z weighted by Z0. So is basically the Z that we obtained here, which is actually Z over Z0. And then we need to multiply it with this Z0, isn't it? So which is exponent to the logarithm of density of states, just the same as logarithm as density of states of 0, times E to the minus energies of 0 divided by T. Okay, so this would be the real Z, the real Z. So then entropy is of course log of this real Z plus average energy divided by T. Is that so? Average energy divided by T. So what is log of Z correct? Well, log of Z correct is we can take the logarithm of this entire expression, and we get that this is log of our Z, what we call Z here in this expression. So it's logarithm of Z, then it's logarithm of this exponent, which is basically just logarithm of density of states minus energy of 0 divided by T. So this expression. And then we said that we need to add average energy divided by T, and we add the average energy divided by T here, and this is it. So this is clear expression for entropy, yeah, we write this expression again: log Z plus logarithm of the density of states at 0 minus energy of 0 divided by T plus total energy divided by T. So finally, we're going to return all these quantities per particle or per lattice site. So total energy per lattice site, specific heat per lattice site, and entropy per lattice site. Well, the reason for this is because these quantities are extensive. So when you have more particles in a system, they grow with number of particles linearly, of course. So yeah, so this is all about thermodynamics. We can evaluate this. Then we are gonna yeah, one important thing here is that before we do this thermodynamics, we should obtain energies. So when we add energies here, we need to have energies for this particular model with this particular n. So n in this case, I think is 20. So whenever we change n, we need to make sure that we recompute energies for this particular model. And I think in the original notebook, I evaluated n for 10 by 10, I think, somewhere at the very beginning when we tested. Yeah, I think here I calculated energies for 10, for a particle 10 rather than 20, and that can result in wrong density of states. But so here I recomputed energies for this n that we're currently using. So it should be correct. Then we are going to take a linear mesh of temperatures. So from 0.5 to 4, let's say 300 points. And then we're just going to store all the thermodynamic relations. So we're gonna call this function thermodynamic relation, thermodynamics, for this temperature, with this density of states, with this energies, and so on. So in other words, now we can evaluate, once we have density of states, we can evaluate all thermodynamic quantities very simply by doing the sum over energies, isn't it? So it's very, very simple. And then we store all these thermodynamic quantities into THM. So we evaluate this, and now we can plot. So here it's a very, very standard thing. We importing PyLab, and then we plot the first column in thermodynamic relation, which is total energy. Yeah, total. So these quantities appear exactly as they were returned from the thermodynamics. So the first quantity is average energy. The second quantity here is specific heat, and the third quantity is entropy. So entropy is something that I added today. You don't have it yet in your notebooks, as far as I know. And then well, we add the labels and we plot the entire thing. Okay, so that's how it needs to look like. So we know that the energy at very high temperature, eventually it will go to I think 0, and then we reduce the temperature. It saturates at -2. Now the specific heat has to have a peak at a transition, which is around 2.2 something, which looks correct. And in particular, the entropy is the new quantity, and you see that it goes to 0 at low temperature, and then at the transition, of course, has the large change because it's second order phase transition. So it has to go through a change, which is diverging, of course, because the derivative of the entropy is actually specific heat. So specific heat is diverging at this point, or basically has a peak in a finite system. So therefore, entropy has to change the slope very quickly. And then entropy at high temperature has to go to a constant. Now, which constant? Well, we have here entropy per site. Entropy per site. So therefore, entropy per site has to go to logarithm of the available states, isn't it? So number of available states per site is 2, because you can have either spin up or spin down. So therefore, we expect at high temperature that entropy per site will go to log 2, isn't it? Logarithm of the number of available states, which is log 2. So at high temperature, we expect that entropy will go to log 2, while at low temperature, we expect entropy to go to 0, because this is a second law of thermodynamics. In the ground state, we should not have any entropy. We should not have any degeneracy left. So, and we can then check, here I printed entropy for entropy at the lowest possible temperature that we have here, which is 0.5. And we see that indeed entropy at 0.5 is very, very small. While entropy at the highest possible temperature, which is 4 in this case, is almost 90% of the log 2. So of course we could take a more precise mesh, or higher temperature and smaller and lower temperature or higher temperature, and we'll see that indeed at high temperature entropy goes to log 2, and at low temperature entropy goes to 0. So that makes us very confident that we did not make a mistake in evaluating entropy, because entropy is constrained a lot. At high temperature has to go to the logarithm of the available states. At low temperature has to go to 0. Okay, so is there any question about this part, about thermodynamics? Is it entirely clear? Too clear? Too obvious? No question? Okay. So is there no question? Then let me talk about homework. So clearly this is going to be, it's clear to me, okay, at least some of you. This is going to be the last homework, because, well, we are near the end of the year. And so it's going to be from Wang-Landau algorithm. So what's the idea? The idea is to estimate the error of the density of states. So actually, we're not going to estimate the error of G of E, which is density of states, because, well, we are not working with density of states really. We're working with the logarithm of the density of states, which we're going to call for this in this exercise as S of E. Actually, I checked the literature, and lots of people call it S of E. It's just the name. But so this is the thing that we're calculating now, logarithm of density of states. And we want to calculate, we want to do it for 32 by 32 Ising model, and we want to estimate its error bar. Now, I'm not going to ask you to do the complicated binning, although this thing that we're going to do is not very different from binning. We're going to do something simpler though. So to do this, we will just run the same Wang-Landau algorithm several times. Let's say 5 times, okay? And of course, each time we're going to start with completely random, well, with different situation, with different configuration. So therefore, 5 independent runs, you can think of it as very good binning. So we are binning for the entire run. The entire run is one bin in some sense. And we're going to repeat this 5 times. Of course, you can still afford this, it's not a big deal. Now, for this particular case, 32 by 32 Ising model, I tested a little bit, and at least on my computer, around 10 to the power of 9 Monte Carlo steps was needed, because 32 by 32 Ising model is relatively large. It's bigger than 20 by 20 that we used here. So we need to increase number of Monte Carlo steps to converge, so that the modification factor goes to 1. Then once we have a series of approximations for logarithm of density of states, which we call SE of E, then you can do statistics on that. Okay, so statistic on that. So how do we do the statistics on that? Well, we can calculate average of this S of E, just as usual. We have 1 over n. N is 5 in this case. And we just average of this density of states that we obtained. So this is now much better approximation to the density of states that each run independently. But then we have this 5 runs. It's enough to do statistics, or basically to ask what is then the error bar associated with each. What is the error bar for these 5 runs? And as we learned before, statistics says that this is the fluctuation, basically S square of E minus S average of E square. But we know that these runs are statistically independent. Okay, this is now important. We know that these runs are statistically independent. So therefore, we know that the error bar we go as 1 over square root of n, where n is the number of such independent measurements. So again, this is known from statistics. If you have n independent measurements, which are statistically independent, then the error bar for that case is this expression. Yeah, and basically we can evaluate this pretty simply by having all this S E of E. I mean, this is one possible expression, of course, which is exactly equivalent to that. Okay, so so we can then, so what do we ask you? I ask you to plot the difference between the average over all 5 iterations and each independent run. So in each independent run, we are going to get logarithm dense states, and you can subtract from it the average so that you see how big is the fluctuation of the density of states. And then you compare this with sigma phi, and you can then at least see whether sigma phi is similar order of magnitude to the fluctuation. Of course, it should be smaller because it has this 1 over square root of n in front. Now, here we still don't know whether our estimation for sigma v is good. We're using statistics, but you know, what if I don't know, our measurements are biased or something? Then we not necessarily have correct statistical error. So how do we check whether we have correct statistical error? Well, I Googled a little bit, and of course I found a paper from 1995, which I showed last time, that calculated the exact density of states for the 32 by 32 Ising model. And they printed, in the publication, they printed the first 10 values of density of states. The first 10 first 10 integers for the density of states, and these are the numbers. So what we want to do now is check whether our approximate numerical calculation is close enough to this exact values. What does it mean, close enough? Well, of course, if you run this for a very, very long time, you're supposed to get exact numbers, but we're not going to get exact numbers because we are running for a finite number of time. But what we expect is that the difference between the exact and our estimation is within standard deviation, or maybe 2 standard deviations, okay, but not 10 standard deviations. So we don't expect that exact value and our approximate value is more than, let's say, 2 standard deviations apart. If it is more than 2 standard deviations apart, then this is very, 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 very uncommon and shouldn't happen. Because, well, according to statistics, this should occur a very, very small probability, less than maybe 1%, something. So we can verify our estimate S of E is approximately sigma v from the exact results. To do that, we plot average S of E minus exact one, which we know now, and we also plot together with sigma for first 10 energies, and then yeah, and this is the second part of the problem. And finally, the third bullet is to calculate thermodynamics by knowing our best approximation for the density of states, or for local density of states. Okay, so that's for the homework. Is it clear what needs to be done? Do you understand? Anybody?
Professor?
Yes?
So when you're asking us to plot sigma E above,
Yes.
about that, so are we plotting that versus the number of iterations?
No, just as a function of energy.
Okay.
Because sigma E depends on energy, isn't it?
Okay.
I mean, I will show you the result now, so don't worry. You will see the solution, my solution first. So I guess it should be very clear once I show you. Yeah, this is a function. Everything is a function of energy.
Okay.
Okay, so yeah, if you don't have any urgent question, I can show you the solution. Okay, so it's going to be easier for you to do. Here is my solution. So first I copied. Well, let me kernel restart and clear output. Okay, so I was just checking that this solution actually works. So first we copy all necessary routines from the previous notebook, which we developed. So I copied this energy, random, prepare energies, Wang-Landau, and then run Wang-Landau. So again, all these routines are directly from the previous notebook, so should be clear. Then this part of the renormalization of density of states is something that we also have in previous notebook. I just turn it now into routine because we're going to need to do this several times. We're going to need to do this 5 times, isn't it, for 5 different runs. So again, in previous notebook, we have done it, except that we've done it only once. Let me show you where. So where is it? Here. So it's basically this proper normalization. We said proper normalization is has to be done so that the endpoints are we have degeneracy 2. So this is exactly the same thing. I turn now into function. So if you give me logarithm of the density of states, then we will correct it and return the corrected logarithm of the states, which is properly normalized. So that's all. This I think is pretty clear. And then, well, pretty much the simple thing. We just run it 5 times. Not a big deal. So from NumPy import random. Turns out you need to do it in flatness. We said, yeah, here we said that n has to be 32. So we are working with 32 times 32 system. So I said that the number of iterations has to be 10 to the power of 9, because if it's much less than that, we don't reach decent density of states. Yeah, okay, I will execute it first, and then I will start to talk, because it turns out the execution does take some time. So now it's already running. So then, yeah, okay, we start to run. It unfortunately does take some time, especially when I have running Zoom. Somehow it's slow. So then what do we need to do? We prepare energies just like before. So which energies are possible for this 32 by 32 system? What is the index for these energies? What is the minimum energy? We select some random configuration, and then we do 5 times what? So we here allocate memory for this logarithm of density of states for 5 possible runs, and each of them has to be as big as the number of energies. So this will contain the logarithm of density of states for all 5 runs. This is our output in this calculation. Okay, so then we run Wang-Landau 5 times in this loop over n, and every time we get logarithm of density of states in histogram, and then we save logarithm of density of states into this allocated array. And before we do that, we renormalize it such that the value in the antiferromagnet and ferromagnet is roughly 2, isn't it? So this RANG-G is this routine, isn't it? Which normalizes density of states, which properly normalizes density of states. So normalized density of states gives you this SE, and again the first index here is just the eth. It stands for the ith run. So first run, second run, third run, and so on. Yeah. So up to now, I mean, this routine is actually slow. We just have one run done, as far as I see, and now it just started to go the second time. So it's going to take some time. Oops, even the first one is not done, I guess. So 1, 6, 1, 2, and goes down. Now it started to do the second time. 1, 6, 4, 8. Yeah. So the second time is now running, but unfortunately it's going to take some time before the 5th one is done. So in this homework, clearly you will need to leave this thing running a little bit. But I mean, if you are nervous whether your code work, reduce this NITT at the beginning. I mean, put it as 10 to the power 7 or something. And then it's going to be very, very quick. But of course, the results will not make too much sense at the beginning. Well, the fluctuations are going to be enormous. Okay, so once this is done, we are doing then statistics. This is all there is to it. Basically, this is the real homework. So we have this SE of E, which is the logarithm of density of states properly normalized. And then all we need to do is to calculate the average over all iterations, and then sigma square, sigma or standard deviation associated with these 5 runs. So I used so-called sum where I specify axis is 0. So what does it mean? It means that we are summing this array. This array psi e is 2-dimensional. So the first dimension is the run number 0, 1, 2, 3, 4, and the second dimension is energies. Okay, and I of course don't want the sum over all energies. I want to have average logarithm of density of states, which is averaged over runs, but not over energy. Okay, because this is logarithm of density of states as a function of energy. So therefore, I want to sum here only over axis is 0, which means that sum over the first components, isn't it? Or the first index, actually, sum over the first index. And then I divide by n here because this is average, isn't it? So now SA is the average of the logarithm of density of states over these 5 runs. And then, of course, I can easily do average of the squares. Okay, it's really not a big deal. So just square this thing and do sum over x is 0. And then once you have the square average, you can also take the average square, isn't it? So this is the usual fluctuation, square of the what is it? Average of the square minus square of the average. So it's these two, and then divided by n, and then square root of this. So again, this expression is exactly the expression that I gave you here, basically this. So s square of e minus s average square of e divided by n. Okay, so this is the same as this square root. Okay, so yeah, so basically we have now as SGM, we have sigma, we have energies average SA and average S2A. So let me see, is this done? Yeah, this is done. Okay, this is done. So we have 5 runs. So let me evaluate this then. Okay, and then I'm plotting. So what we said we should plot. We should plot the logarithm density of states minus the average of the logarithm density of states, isn't it? So which is SI minus average S. And then also plot sigma so that we see that they are of the same order of magnitude. Okay, so not a big deal. So what do we see? Yeah, so the first run that has density of states minus the average is the blue curve, then is the orange curve and the red curve, green curve, and so on. So of course they fluctuate. And we see that the sigma indeed is of the same order of magnitude, but it's smaller. It should be smaller for 1 over square root of n, doesn't it? So sigma is this, is the or our estimated sigma. And then, of course, this doesn't tell you whether we calculate sigma correctly. It just tells you that we implemented this trivial formula correctly, isn't it? This trivial formula of this S minus average square. Now, in order to see how close we are to reality, we take from the literature the exact density of states that was given. Okay, we evaluate this, and then we plot the exact density of states. This logarithm, we have to take logarithm of this G exact. For the first, we have only first 10 numbers, but that's good enough. Then we plot our best estimation for the density of states. This is SA, which was just calculated above. So this is average of logarithm of the states is SA. So we are plotting our estimated logarithm density of states for first 10 energies, and then we check the difference between exact and our approximated logarithm density of states. Okay, so let me evaluate this. And so what do we do? What we see is this S exact is the blue curve from the literature. S numeric is the orange curve, and the difference is the green curve. So clearly they're pretty close. Of course, you see also some deviation, which is normal because the density of states was not running for such a long time. But nevertheless, you clearly see that these two numbers are reasonably close. So on the plot, they kind of appear more or less on top of each other. Okay, so that gives you already some confidence. But then finally, we're supposed to compare the difference between the two. So we already have the difference. Here's the green curve. Now this green curve should be of the order of sigma, isn't it? That's now the real check. So RD2 of the order of sigma. So the blue curve here is our best estimated S average S of E, or numeric S minus exact is the blue curve, and our estimated sigma is the orange curve. And as you see, our orange curve is of the order of 0.1, and our error bar is of the order of 0.18. So this is actually a pretty bad case. So most of our points are within 2 sigma. It's still okay. 2 sigma is fine, can happen. When I was running it earlier, actually sigma was above this S of E minus S exact. So sometimes it's above, sometimes below, sometimes similar order of magnitude. But as long as it's similar order of magnitude, it's fine. So right now, our result is within 2 sigma, which is fine. It's more common that the two curves are on top of each other. And well, right now they're not, but that's okay. So when you check this, I expect you to see these curves to be of the similar order of magnitude, that's all. Okay, so once you have this, we have, so now from now on, we're going to only use this average density of states, or the best density of states we have, and we're going to do now the thermodynamics. So this thermodynamics is exactly copied from the previous notebook, so nothing new. Of course, there is something new here. I added entropy, okay? But entropy, you saw the derivation, and you saw my calculation for it. So this is exactly the same as before. And then again, I take some linear mesh of temperatures, 300 points, and evaluate thermodynamics on all those points. Okay, and then I plot this. And now we have solution for the 32 Ising model, average energy, which goes to -2 at low temperature and close to 0 at high temperature. Entropy that goes to 0 at low temperature and log 2 at high temperature, and finally specific heat that has a peak at a transition 2.2. So this is all. This is the homework. So is there any question about the homework? Is it simple? Too simple or too hard?
Not too simple.
Not too simple. Okay. Well, homework shouldn't be too simple. Yeah. So once more, this is the homework, and now what's the deadline? I mean, usually I give 1 week, so it means that you should be able to do this at the very beginning of May. And once you return this homework, I guess I'm going to give you the grade. That's that. So please do it as soon as you can. Now, what else are we going to do here in this lectures? Now, I have 2 other little subjects which I wanted to introduce. Basically, I'm not going to go into details with both, but maybe just one. Both are related, of course, to Metropolis. So we use Metropolis now just to simulate Ising model and to obtain many-body density states with Wang-Landau. But of course, Metropolis has lots of other uses. One most well-known is finding minimum of a very high-dimensional function. So minimization of a function. And then finally, one less known but still important is integration of high-dimensional functions. So this integration of high-dimensional functions we already did with Vegas, but this is different in the sense that it's simulation by Markov chain, which is also possible. But I will probably first concentrate on minimization because this seems to be much more standard thing that you can see in typical numerical books. So the problem of minimization. So let's say that you have a 1D problem. So let's say that your function g of x, so this is the function that you want to minimize, has this complicated shape. I mean, if it has just one minimum or a well-defined minimum far from other minima, then the problem is completely trivial. We don't even mention it. But what if you have so complicated function with lots of minima, local minima, okay? So this function has 1, 2, 3, 4, 5, 6 local minima, maybe seven local minima. So if you have lots of local minima, then what would you do? So what we require is to find the global minimum. Okay, global minimum. That's what usually, almost always, we have a problem of finding global minimum of a function. Now, if the problem is 1D, then there is an obvious solution. So how would you approach that? Any idea? You have a one-dimensional function, and somebody asks you to find a minimum of it, global minimum. How would you do that? Any idea? Let's say I give you for the homework. I give you some polynomial or something. Polynomial plus some transcendental function, so it's not completely trivial. So what would you do? Yes?
Use the gradient method.
Which one?
Use a gradient method.
Gradient method. Sure, that's for sure. Gradient method is definitely a good idea. But the problem is that if you use the gradient method from here, for example, you're going to end up in here, in the local minima. So, I mean, when we were introducing SciPy, there were lots of those routines which were called minimization routines, isn't it? So minimization routines, what they use is some type of gradient method, yeah, gradient search. So, and then what they require from you is starting point, x0, isn't it? So let's say that you give x0 here, this will end up in this minimum. If you give x0 here, it will end up in this minimum. If you give it here, then it will either end up here or here, somewhere, depending on numerics. But whenever you give me a point on this curve, I can immediately tell you where will the minimization end up. Okay, so and if the curve is not simple, then you have to be a bit more careful to find the global minimum. Well, the solution is trivial. Well, you plot the function. Okay, so it's one-dimensional function and it's not too hard to plot. You just plot it. You see that the minimum is here, and then you give any point which is close enough to minimum. You don't need to be very, very precise. You just put a point which is not too far from minimum, and then you use one of those available minimization routines, and you will get a global minima. So again, you can do the same thing even for very high dimensional functions. Even if you have, I don't know, 10-dimensional function, you can still use this gradient method from SciPy. If you have some idea of where the minimum is, or if you don't care whether it's local or global minimum, then of course you also can just use this downhill gradient search. But the trouble is that many times when you have lots of minima, then you might be getting just another local minima, which has nothing to do with global minima, doesn't it? So now again, for 2D and 3D functions, the problem is still usually it's still better, of course, to plot the function, or equivalent thing to plot the function is to estimate it in sufficiently good grid, isn't it? If you estimate it in sufficiently good grid, then you have a sufficiently good idea of where the function will have a minimum. But that's more or less like the same as plotting. So in 2D and 3D, you can still plot. And then once you plot, you can see more or less what the global minima is, and then try to estimate. I mean, if you have lots of local minima, which are almost degenerate, another way to do it is to, after you plot the function, you just calculate several local minima. I mean, you start somewhere here and you get the exact local minima. Let's say that the function that you didn't have, if you have a finite number of points, isn't it? Let's say you have point here, you have point here, you have point here, you have point here maybe, and here, then you would not see the exact shape of the function, isn't it? So you might miss a little bit the shape of the function. So then you might just estimate with downhill method. You would estimate this minimum here, and you would say, whoops, minimum is here. Then you estimate that minimum here, that minimum here, and that minimum here, and you compare them, and you see the global minimum. That's also completely doable. And the same procedure can be done in 2 dimensions or 3 dimensions, of course, to find the global minimum. It's completely brute force, nothing that would need further discussion. However, when you have very high dimensional problem, then there is no hope to plot. Does not have 100 dimensions. How do you plot a function in 100 dimensions? You can take a cut in 3 dimensions maybe, and then another cut in another 3 dimensions. But I mean, that looks like almost impossible problem. However, there is something that is it's kind of standard solution is by simulated annealing. Okay, so let me explain what simulated annealing is. It's actually very, very simple. You will get it in no time. So our objective is this function f of x1, x2, x3 to xn. So n is large. We have function of several variables. Okay, we call it f of capital X, where capital X is a vector. So then what you do is you do metropolis random walk with probability distribution or density rho of x, which is Boltzmann, e to the minus f of x, where this f is based, this function is now like energy. Okay, so we just declare this function to be our energy, and we use Boltzmann distribution. Okay, so that's all. We just use this as our weight of the metropolis. And now the only question is, of course, here what to choose for the entropy, and why would this give you a minimum? Well, here we use physics somehow. So we start with a very high temperature, T goes to infinity. And when T is infinity, we know that all configurations are equally probable, because this thing is 0, so rho of x is flat. But then we slowly reduce the temperature, and then when we reduce the temperature sufficiently slowly, then we know in physics that the system should find ground state. Ground state meaning the state with which has the lowest energy. So again, why is this the case? Because in the ground state, we know that this f will have the smallest possible energy. F will have the smallest possible value, which means that this exponent is going to be the largest. Okay, so the contribution of the exponent when f has the minimum value is going to be the largest, and therefore, of course, we are going to end up in that state which has the largest possible probability. Okay, and provided there is some little gap between the ground state and excited state, we're going to end up exactly in the ground state. Otherwise, we're going to end up close enough to the ground state. So this simulated annealing does not guarantee you to end up exactly in the minimum. So we are not going to get exactly in the minimum, but we're going to end up hopefully close enough to it, like within the range of which this range is related to temperature. Okay. Of course, if you have discrete system, then there is the discrete system would have a gap, and then we are guaranteed. Well, we're still not guaranteed to get to the ground state if the degeneracy is high. Well, there are actually several issues here. So simulated annealing says that we are going to get to the ground state provided that you choose the temperature so that you reduce the temperature sufficiently slowly, and that yeah, basically this is it. So the cooling down should be sufficiently slow in order to get the ground state. So of course, if you do it very quickly, then non-adiabatically, we know from physics that the system could be stuck in a local minimum. But if the cooling down is made sufficiently slow, then from physics we know that we're supposed to end up in ground state. Now we are going to implement this simulated annealing for so-called traveling salesman problem, which is a relatively straightforward problem. But before I do that, I would like to introduce another idea, which is integration by Markov's chain, which again uses the same idea of Markov's chain, but does something else. It does integration of the high-dimensional function. Now, why do I do that? Because it's kind of, in order to contrast this method with the previous method of Vegas that we developed. So you can use not only Vegas, but you can also use Markov chain if you want to for integration. Now, naively, we would say, what's the big deal? I mean, I can use my function f of x as the weight in the Markov chain, and I sample for a long time, and eventually I should know what the integral is, isn't it? That's what you would normally say. Well, not quite true. Oops, I forgot to. Yeah, so not completely true. So basically, when you sample for a long time, a function like that, you would know everything but the total integral. So yeah, here are some notes on this problem, and yeah, so I forgot to write one important equation, so I'm looking back to find the equation. But anyway, the point is the following. So there are two ways to do this Markov chain simulation. One way is to define an alternative function. So we have the physical space. In physical space, our weight is just our function f that we're trying to integrate. Okay. However, we have an alternative space in which the weight function is some known function which can be normalized. Okay. So and then the idea is that we are allowed to jump between the spaces. Okay. And this, how often do we jump, is determined by some number which we call V naught. Okay, so that's one way. The alternative way is is the following. We actually take Markov chain with probability that it's the average absolute value of the function plus some constant alpha. So this constant alpha is an arbitrary number of the order of 1. It can be of the order of 4.1, let's say. So, and then approximately 0.1, of course. And then we add to this a function which is normalizable. Okay, so actually, no, this is not the best. So basically, this alpha should be actually what I should do is the following. So this alpha is an arbitrary number, is a number, but we should add it in such a way that our final, that the time spent, no, actually not true. So we need to do it in such a way that the integral, the final integral of the function f of x has to be of the same order of magnitude than the function fm of x dx. So why is that the case? Well, the point is, if we, let's say that we set that the probability is only average value of f of x, that would be great. The problem is that in this case, we will see later on that we have no clue about what the integral is. We could get projections to all possible dimensions of the function, but not the exact integral of the function. Now, if we choose the probability to be only, if we remove this part and then only take this part, then we are gonna sample this auxiliary space. Now, provided that this fm function is close to function f, we are still gonna get a good approximation for the integral, but this is not as efficient as if you take that this part of the function has bigger weight. So the first approximation, what we want to do is we want to move into this, in the space of this function where the weight is roughly average value of function of x, but we add to this weight a little bit of the absolute value of some other function which is known, for which we can numerically integrate. Okay, so we would like the first approximation to just use this in Markov chain. We take that probability for the function is the absolute value of the function, but this will not give you the integral unless you add to it some small weight of another function which we know how to integrate. Okay, and then if you have such a probability, then we will derive what is the integral of the function. Now, what are the important properties? So this function fm has to have the property that it's numerically normalizable. And we can also take, without any loss of generality, we can take that this function is always positive. So without loss of generality, we can take it's positive. But now, of course, if this function fm is an arbitrary function, then our simulation will be very inefficient. What we want, of course, that this fm here is sufficiently similar to f of x, the same idea as in Vegas algorithm. So this this extra function that we add should be similar to f of x. And for example, one way to make it similar is to say that function fm of x is just the product of projections to all the dimensions. So this is exactly equivalent to what we did in Vegas. So we said our fm of x is the product g1 of x1, g2 of x2 to gn of xn. And then, of course, because we write the function to be this product function, then it's very easy to integrate it. This is exactly the same thing as Vegas. So the integral over the entire dimensions is just the product of the integrals of the functions. Now, in this case, of course, now the question is what are these g1, g2, gn? And in this case, we used basically the same thing as in Vegas algorithm, or almost the same. So basically, these one-dimensional projections of the function are really just straightforward projections of the absolute value of x. So we sample absolute value of x. Whenever we visit the configuration, we take the absolute value of function f, and then we take this delta function. So basically, we just monitor the projections of the function to all axes, and then we construct a weight function like that. Okay, so then fm of x is basically a function which is similar to the original function, actually similar to the absolute value of the original function. However, it's simplified in the sense that it's just a product function. Now, you would ask maybe, why do we do that? Why don't we use Vegas? I mean, we spend so much time to derive Vegas algorithm, which looks like exactly the same as what I've done up to now. And the truth is, well, yes, this gives also performance which is almost identical to Vegas, or maybe slightly worse even. So why is that useful? Well, the usefulness comes from the fact that in this case, we can construct this function f. We have more freedom in constructing function fm. So this fm function could be more general convolution function or any other type of function. So for example, we could decide that the function fm is not going to be just a simple product function, gi xi product over all I not equal to the j times gj xj. So for example, this part here is now just like before, a product function. So you see, because this product I not equal to j, sum over j, actually then we can take any j if you want to, doesn't matter which one. So if we do just this part and no h, then this is exactly the same as before. It's just the product function over all dimensions. But now what we can do here is we can add here another function, hij of xj minus xi, which is convolution. So, and convolutions are very, very common in physics. So lots of functions tend to be convolutions of something. So that's very, very common. So this freedom that you choose a function which is more physical or closer to physical functions, it's very useful. So therefore, if you choose a function like that with convolution, and it turns out that this function fm can still be, it's still normalizable. Okay, then because it's normalizable function, we can use exactly the same algorithm as before. So now, but then you might ask a question: what is this hij? Well, the best solution, of course, for hij is basically just to project the absolute value of the function on the diagonals rather than on the axis. So this one, this gi is basically just projection of our function on the axis, isn't it? So we discussed in the Vegas algorithm that this is just a projection, as the delta xi minus yi tells you that we are projecting function f on all the possible axes. But you can also construct this h here, which is projection on the difference, okay, of the two axes, which is diagonals. Okay, so in this case, we are actually projecting our function on all possible diagonals, and then construct the function from projections on all axes times projection on all possible diagonals. So now, if the function turns out to be peaked either on the diagonals or on axis, along the axis or along the diagonals, we can resolve this with this Metropolis algorithm. So the Metropolis will now go not only to the function, if the function has divergences along the axis, but we'll also find all the divergences which are not along the axis, which are along the diagonals, and also even if this alpha is small compared to, let's say, much smaller than 1, then we are going to also sample space where function f, absolute value of f, is large. Okay, even if this is somewhere completely away from any diagonal or any axis. Okay, so that's the idea of this integration by Markov chain. So to summarize, the idea here of integration of Markov chain, in some sense, it's similar than Vega's algorithm, except that we are moving with Markov chain with this probability of absolute value of f of x times adding to it some small part of some design function or fake function, which this function has the property that we can numerically normalize it, and it's sufficiently similar to absolute value of function f of x, and this sufficiently similar, but it's still integrable. So either we take the function to be just the product over all dimensions, or we take the function to be convolutions. Of course, other choices are possible, but these are the two which are kind of most common or most obvious. Okay, so I don't plan to go further into this details on integration by Markov chain. I now plan to go to this minimization of a function by simulated annealing. So, but before that, I want to ask you if anybody has any question on that chapter. Is there any question? Or is this so obvious or it's so hard? Any question? No question? Okay, so I see that the time is already 6:20. So definitely not obvious. Okay, good. Yeah, so time is 6:20. So for today, if you want to ask a question, you can stay here. I will stop recording right now.